We are going to talk about continuity is the big thing for today, and then we're going to talk about some one-sided limits, which are going to be pretty straightforward. It's going to be like the limits we've already done, except for half as much work. So that's nice. Continuity. The idea of continuity is if I have some kind of graph that's out there, if I can draw the entire graph without lifting up my pen, it's considered to be continuous. Okay. So if I've got some graph, there's my graph, and if I were to graph something like this, that was said to be a continuous function. Okay. An example of one that's not a continuous function would be one like if I have an asymptote here, for example. Go like here and like here. So I can't draw the entire graph with my pen without lifting up the pen. Okay. So this is said to be not continuous, and there's a couple different kinds of what they call discontinuity or functions that aren't continuous. This one's continuous everywhere. They say continuous across either the entire interval or from negative infinity to infinity, or all real numbers. This one's continuous pretty much everywhere except for at this one line right here, and whatever that happens to be, -1, -2. So it's continuous everywhere but at that point right there. Okay. So that's kind of the basic idea of continuity. Now, if it's not continuous, there's two different kinds of what they call discontinuity. There's removable discontinuity, and then there's non-removable discontinuity. So, continuous are pretty straightforward. You can draw the line without lifting your pen. You're good. It's continuous. Okay. If it's not continuous, there's a couple different kinds. One of them is called a removable. Removable. I spelled that wrong. There's no E in removable, is there?
No.
It looks wrong. Removable.
I just went right either.
That doesn't look right. I think he is right for some reason. Someone want to look it up? You guys don't care that much. Removable continuity. Discontinuity. Okay, so there's two kinds of discontinuity. One is called removable discontinuity, and the other is called non-removable discontinuity. So a removable discontinuity is basically this. I've got some graph that might look something like this. Who cares what it really looks like? But at some specific point, let's say there's a point right here, I have a hole right there. Okay, and we've seen graphs like this before. But if I'm missing a point right there, missing some kind of hole, that's said to be a removable discontinuity. I.e., if I were to take a point and plug in that hole right there, it would now be continuous across the entire thing. Okay, so if you can just take one point and basically fill it in, that would be considered to be a continuous function. So they call that a removable discontinuity, is that I basically just pulled one point out. Okay, now if I pull the point out and I move it, you've seen some graphs like this where they move the point down below, that's still a removable discontinuity. They still have this function right here is continuous, except for that one point that I just pulled the point out and moved it. Okay, so they call that remove. What's that?
There's no E.
There's no E.
Nope.
Thank you. So it's just. Gosh, it doesn't look right. Removable. We'll say removable from now on. So. All right, so removable discontinuity. You just basically can take a point out or not. That's pretty much what you're doing. So now non-removable is you're doing more than just taking a point out. So for example, a non-removable. Removable. Non-removable discontinuity is a little bit different, and that's kind of like the one that I drew up above. It's basically they're not taking out a point. You actually have to lift the pen up, go to a different spot, and then redraw somewhere else. So one that's not a non-removable discontinuity, so I have a graph that comes up something like this. And then I've got like an open circle here, a closed circle there, and then I come down here and do an open circle, and then finish it out with something like that. Okay, and that right there is what they call a non-removable. Okay, this is continuous on every part except for at this point right here. So if I go out from this side right here, it stops, and then I have to literally lift the pen up, go to a different spot on the graph, put it back down, and then keep going from there. Okay, so that's non-removable. Okay, I didn't just pull a point out. I literally moved the graph and did bad stuff. Okay, so those are the two common types of discontinuity that we'll have, either removable or non-removable, and that's pretty much it. So a lot of the stuff that we'll be doing will be looking at graphs today and deciding what kind of discontinuity it is, and then go from there. Okay, so that's continuity, pretty simple, pretty straightforward. The one-sided limits are kind of the big stuff for today. So let's take a look at one-sided limits, and let's do this one right here. Let's say I have the function f of x equals, let's go the square root of 4 minus x squared. Okay, first off, go ahead and graph that, and then see if, one, you think it's continuous, and then two, where you think it's continuous at, or if it's not continuous somewhere. So throw that on your calculator. You guys getting a part of a circle? Okay, good. You guys get that? Hopefully. Yeah, cool. Sounds pretty good. So let me just draw it real quick right here. We'll just go out about 2, looks like. And then how far does it go up? 2. Circle here. Okay, so that one they say it's a continuous function. It might be nice to think about the domain, like all the possible values I can plug in there. The domain is pretty much going to be the values from -2 to 2. I can plug in any of those values that I want. I can't plug in any number bigger than 2 because that would give me a negative number on the inside here. And I can't plug in a number negative or bigger than negative or smaller than -2. That would give me a negative number on the inside as well. So my domain is pretty restricted here, and I'm continuous along this entire region right here. So if I'm continuous, I want to find what they call one-sided limits. Now, the limits that we've done so far have been pretty straightforward. Like, for example, limit as x goes to 0 of our function f of x. Okay, so what would be the limit as this x approaches 0 of our function? What do you guys think that's going to be? 2. Okay, everybody okay with that? We get 2. Now, just to refresh your brains, in case you're a little off, the limits, you approach it from both sides. And so you have this, we're going to 0, so we would go towards the 0 on this way, towards the 0 on this way, and then if those two arrows run into each other, that value is our limit. Okay, so the limit is we're getting closer and closer to one specific number. Okay, now what if I did this? What if I took the limit as x was going to 2 of our f of x? Erase the zeros here. Anybody got the answer yet? It's kind of weird, right? Are you coming at it from both sides? No, right? The x value that we're looking at is this point right here. That's the point that we're actually looking at, okay? And fortunately on this one, you could do a direct substitution. You could literally just plug it in and get the answer, okay? But the limit actually might not exist for this x equals 2 right here, or as x approaches 2, because we can't really use the formal ways that we've done limits so far. Normally we'd come at it from this direction right here, and then come at it from the other direction. But there's no graph to follow along or trace to get towards that point. So they call this a one-sided limit, a limit that you can only come at it from one side. Okay? So we're only coming at it from this right side right here, or from the left side right here. And how we denote that is that actually it looks exactly the same as this. They just say that we're going at x goes to 2, and we're coming from the negative side. So they put a little negative up on the top there. It looks like an exponential type thing on the inside of that, so it's pretty small. But that tells you which side you're coming at it from. Okay? So on this one, we're taking the limit as x approaches 2 from the negative side. Okay? That means from the smaller side, which is on the left. So from the negative side, we're just attacking it from one side. Now the weird part about this is I don't have two arrows that are going right at each other. I've just got one. I've just got one arrow, and I'm just trying to see what number that's getting closer and closer and closer to. Okay? So the answer for this one, if it's a one-sided limit from the negative side, from the left side, that's going to equal y value of 0. So the limit of that one is going to equal 0. Okay, now if the negative weren't there, we actually couldn't do that limit. We couldn't come at it from both sides. Okay? So that's one option. That's one type of a one-sided limit. Another one to look at, let's say I did the limit as x approaches negative 2. And this one I have to approach from the positive side of my f of x. Okay, I can't really approach this one from the left side because there's no graph over there. There's nothing to trace or to follow along. Okay, so I've got my f of x function. I'm going to the negative 2 value, which is I'm looking at this point right now, which we can't just do direct substitution on this one from our one-sider. And we're coming from the positive side, which means we're going to go at it from this direction. We're getting closer and closer to the value of 0, looks like, so our limit for that guy is going to equal 0. Okay, so that's what they call a one-sided limit. Just comes from one side. You don't actually have to match up two sides to make them run into each other. Okay? Pretty easy. Pretty straightforward. Okay. Now the nice part is we've pretty much done these one-side limits already. We've pretty much found the limit from one side getting closer, and we've done it from the other side. And if you have the limits matching on those from the positive and negative, then the full out limit is going to exist there. So, although this one's different numbers, so we can't really. All right, let's do one real quick. It's called the greatest common integer. Have you guys seen that one before, by chance? Let me show you how to graph that. You guys seen that funny looking bracket before? Mm-hmm. Yeah. I'm going to show you how to graph it on your calculator, which is nice. Okay, so as I graph this, if you don't remember what this basically is the automatic round down, which is, it's like bad rounding. That's what's going on here. So if I were to take the greatest common integer of, let's say, 2.6, for example, that equals 2. Okay, it's almost like truncating it. You're just taking the last number off. You're rounding down to the next number. Okay, if you were to do like the greatest common integer of, like, let's say, a negative 3.7. Right? You go down to the next number. So if you round it down to the next number, what would that go to? Negative 4, right? It seems kind of odd to go negative 4, right? It's kind of weird, huh? Right? Because you got to go down. You got to go down to the next number. Put that on a number line, right? If you thought about putting that on a number line, right? You got 0 right here. If you went negative 123.7, right? You got to go down to the next number. The next number down is negative 4. Okay, so that's negative 4 right here. 2.6 was 2.6. We go down to the next number, which is 2. So automatically it bumps it down to the next value. Okay, so that's what they call the greatest common integer function. Anyways, what the graphs look like is actually pretty cool. If you go on your graph, I can show you where that is. Ooh, matters a lot. Y equals, clear that guy out. V and your Y equals when you're doing this, but if you go to the math function, and then over to the numbers, so you go over to the right. Oh, why is it not showing you guys? Okay, that was weird. I don't know why it wasn't doing it. Anyways, we're going to now go over to the numbers, and then number 5 looks like it says int, that stands for integer, so it's taking what they call the integer function. So that's going to be the greatest common integer. So you just type it in like so, and hit graph. So you guys have probably seen that before.
What do you plug into it?
Oh, why is it being weird? It's just like it turned it off. Seriously, might be better. Might borrow somebody else. So that's my Y equals. I'm afraid to push any buttons. Just make it weird.
Mine's got an error.
Weird.
Sweet.
Oh. I kind of want to use yours. Is that okay? I'm sorry. Can I? Use mine. It's broken. but you could use it. So that's what the Y equals looks like. Is that what you got? Okay, we'll have to mess with it then.
Oh, yeah. Wait, what?
Yes.
I did exactly that. Like, last one has an error.
Does it say what the error is?
That's not what I meant.
Then it doesn't look just like that. It did? It doesn't anymore?
No.
That seems like... Zoom 6 and see what you get. Was that the negative version of it, right?
No, it's, yeah.
Yeah.
And then 1.
Oh, and then...
What's this?
Lots of with asterisks.
Alright, anyway, so let's go ahead and grab... Fine. Go to...
I found
Oh,
what
did you have a
makes
plus sign?
these
I don't know why.
calculators so
You have a plus
expensive.
sign.
Check this out.
Thank you.
Well, if you go to draw, second draw.
Okay, now you guys were making fun of me for
Program,
pausing the movie
then
to do math.
Smash it over here.
Okay, there you go. There you go.
Always
There
send
you
me
go.
math class.
Go down.
There you go.
Wait, what did you talk about?
Okay.
And then
I don't know.
once
We'll
you
have to
wanna
find yours. I don't know where yours
clear
is. You got the odd calculator. I'll figure it out. So.
until you
Anyways, all right. So this is what a graph looks like. Everybody should have a graph look something like that. Now basically you can plug in a couple values here. If I go second calculate value, you can type in the value x equals 0. Right now, if x equals 0, we get y is 0. That means we have a closed point right there, 0, and we're going to go all the way over to 1, and we're going to have an open circle on 1. So we'll have an open circle on 1. Okay, if I were to try to type in the value, x is 1, right? Notice it jumps up to the next graph. Okay, so the 1 value, it's hard to see, but basically you have open circles on the right bottom sides on all of those. Okay, so all these are open circles all the way through. You guys okay with that? Okay, so because once it hits that value, it bumps up to the next value. Okay, so we're going to have a flat line. It's the same number all the way through until it gets to the next value. Same number, it bumps up, so on and so forth. So it's going to be like so, up at 1, and we're going to go over to 2, so like this. Up another one, so we're going to go like this, so on and so forth. Okay. Now, if I were to do some limits of this guy, let's go ahead and take a look at some limits. We're going to do some one-sided limits of this. If we take the limit of this function, let's go as x approaches x value of 1, and let's do it from the negative side of our g of x. Okay, so I'm taking the limit of this function as x is going to 1, positive 1, from the negative side, from the left side now. Okay. Well, positive 1 is right here, right? This is my value. As I approach this x value, I'm approaching this value right here. As I'm approaching it from the left side, I'm getting closer and closer and closer to this value right here. So what number am I approaching right here? Y value is 0, right? I'm approaching 0 for my limit there. Okay. So as I'm approaching this value, I'm approaching this value of 0 right here for my height. My height is 0 at that point. Okay. Now, if I do the exact same limit as x approaches 1 from the positive side of my g of x, that just means approach it from the right side. Okay, so we're approaching this graph from the right side now, and we're approaching from the right side of this value of x is 1. So I'm actually approaching it along this graph now, and this value is getting closer and closer to what value? 1. Okay, so the limit of this guy equals 1. Okay, so our one-sided limits can be different, especially if we have weird functions like so. Okay. Now, what's the limit of this guy as x approaches 1 of g of x? Doesn't exist. Okay, in order for a limit to work, both the one-sided limits have to approach the same number. If they approach the same number, then the limit of the actual number from either side is going to be whatever the value is. Now, if they don't approach the same number right there, which we've kind of already talked about that concept, then it doesn't exist. Okay, those numbers are different, it doesn't exist. Okay? Does that make sense? Are we feeling kind of okay about this? It's not too bad. One-sided limits are just like the other limits. You just come out from one side. Okay, cool. That's it.
Or you can shade the top or bottom of your
What? I love funny I was watching the
That's how
I never. Oh my gosh, it took me so long to understand this.